Okay. So we had some exercises to do. What do you think? The first one was the stability. Easy, right? No problems? Problems? Yes or no? The second exercise, to derive the vorticity equation. We have done that already, but now we're using a slightly different version of the momentum equation. Many terms cancel each other out. Were there any problems? The thermal wind equation. This, so how does that work? Should we do this together just to see? So in our pressure coordinate system, our geostrophic wind was minus 1 over F naught d phi by dx dy. And Vg so what do we do to derive the thermal wind? We calculate the derivative with respect to p, with our vertical coordinate. Actually, this can also be done, of course. We can derive the thermal wind equation in the z coordinate system. But then some additional approximations would be necessary to get to a simple form. The pressure coordinate system is actually strictly possible. So we apply d by dp to both equations. So what do we get? D ug by dp equals minus 1 over f naught. And here we can reverse the derivatives. D by dy, d phi by dp. And we get dvg by dp equals 1 over f naught. In the same way, d by dx, d phi by dp. So what do we do now? Hydrostatic equation, the one that was given, d phi by dp equals RT over P, right? Minus sign? Yes, minus sign. If we insert that here, we get dug by dp equals, minus goes out, 1 over f naught, dy dy, r t over p, and dv g by dp equals 1 over f naught minus sine d by dx, rt over p. So how do we get then to, what justifies us now to say this is r F naught P dt by dy, and this is minus R F naught over T by dx. Is this equation correct? Yes. We can take out the P. Why? Because it's an independent coordinate in our pressure coordinate system. This is taken a constant P, this derivative. So P, the derivative doesn't act on P. So that justifies this simplified treatment. If we do the same calculation in the Z coordinate system, we have to make an additional approximation. The final version in d by dz would look very similar in the approximated way, but in pressure coordinate system we can actually derive an exact formulation, which is quite nice. As I mentioned before, this is a very useful relationship. It's the first order approximation, because we use hydrostatic, is very good approximation, but geostrophic 10%. But still, any kind of jet flow you will see will, to a first order, obey this equilibrium. So it's very useful to know this. And as I also mentioned, sometimes we can think of kind of temperature gradient is provided by external forcing, but it's not always 100% sure. This is just an equilibrium equation. So it could also be that the jet flow is provided and then the temperature has to adjust in this equilibrium condition. It's a quite interesting relationship. It is valid for all kinds of jets that we find, even in the tropics. In the tropics, okay, the tropics is the problem, of course, is that particularly at the equator, this Coriolis parameter goes to 0. But as soon as we are, let's say, 10 degrees north and south of the equator, this is already a valid approximation. We will see this in some later lectures. Today, no, there are more exercises, important ones. So the estimation of the divergence by using the vorticity equation. Because I explained to you in the past there has been this problem. How do we estimate divergence from wind measurements? Not easy to do. A more kind of perhaps more accurate way to do it is to use the vorticity equation actually. And as an exercise you had to do this. What is the final value of the divergence in exercise 2.3? Let's see. The value I have for dUA by dx plus dVA by dy is 3.10 to the minus 6. This one. Because, so what do? You insert all kind of values that we have into the vorticity equation. So what was the trick? If the wind comes from the southwest with a certain wind speed, that means we can estimate the velocity components from that. So what are the velocity components? There were, same for UG and for VG, 14.1 meter per second. The vorticity component were minus 4 over square root of 2 times 10 to the minus 11, that is the gradient of the vorticity, and so on. Beta over F naught can be estimated by the radius of the Earth, and so on. So does someone have this value? Can you confirm this? No?
Yeah, 1.6, 10 to the minus 6.
1.6. We have to converge on some common value. This is clear, no? The equation to be used was just the and we had information for all of these: vorticity change, local vorticity change, Coriolis parameter. We know the latitude where we are, the advection velocities, the geostrophic ones. We had given the gradient. We had given how the vorticity changes. So no problem here, in principle, apart from inserting wrong numbers. What about the next one? Even more interesting. We have the vorticity equation and want to derive from that, it's the same thing essentially, the vertical velocity. Divergence is related to the vertical velocity. But now it's even more interesting because we have given a geopotential height field, a wavy propagating geopotential height field. And we should be able from this propagating wavy geopotential height field to estimate where we have omega present and where not. So what is the final solution for that? It's the same thing, no? You insert you have an analytic expression for the geopotential height field with some parameters, and then you know that the vorticity is the Laplacian of the geopotential height with some scaling parameters. And the velocities are the gradient of the geopotential height, so we can calculate everything from this and insert the vorticity equation and calculate the vertical velocity. Right? So obviously the trick was to use the omega by EP, again the divergence, equals to same equation as before. And then we simply have a given phi field, and we know that the vorticity is equal to 1 over f naught Laplacian of phi. Once given this, we can calculate the Laplacian. The velocities we know is the gradient of the phi field. So if we insert all this, you get an expression for dW by dP, right? This is some expression based on the parameters of this propagating wave. So I've got here V over F naught times cosine phi P over P naught cosine K x minus Ct, so this propagation, and then here comes some term K square C minus U plus beta. Do you have this? So what do we do now? We integrate with respect to the vertical coordinate. So the only thing that depends on the vertical coordinate is this term here. So what is the final result using the upper boundary condition? Omega from P equals V k squared C minus U plus beta divided by F naught pi 0 P0 over pi cosine k x minus ct, and then the sine from pi t over t naught. This is intuitively, for everybody who studies dynamic metrology, intuitively this is okay, because the vertical velocity should be smaller or close to zero, close to the boundaries. It should be maximized in the middle of our height. So that the sign would provide that. That's okay. Secondly, with respect to the geopotential height field, we are 90 degrees out of phase. So whereas the geopotential height field was varying with the sine, now we are varying here with the cosine. So we find the maximum vertical velocities not under the ridges and troughs of our geopotential height field, but just where that has the kind of the node. And also pay attention to this here. There's one case when the vertical velocity is actually zero. And this is the phase velocity for Rossby waves that we will derive in this lecture, actually. And so everything is consistent. For the waves that we derive today, we assume that the divergence term that is related to the vertical velocity is zero. Therefore, in this version, that's the condition for the phase velocity of divergence-free Rossby waves. Before we derive the Rossby waves today, we want to have a look. Essentially, we will derive the Rossby waves, these large-scale waves that we have discussed already. We derive them from the vorticity equation. And there's a reason for this, because it filters out some other wave types. Because if we write down our momentum equations for let's say for our barotropic shallow water system, which we have used before, plus the hydrostatic equation, of course, minus d phi by dy. And then we have the equation for the height of the system. If we integrate the divergence-free equation in the vertical direction, so we have dw for our shallow water model equals to minus the horizontal divergence of our velocity vector. We integrate this in the vertical. That gives us then essentially the height change of our system equals to minus height itself. These are independent of height in our shallow water model, times the divergence of the velocity. Or if we multiply this with g, we get our phi. So this complete system of equation, these two plus this, are called shallow water equations. And as they are, without applying any vorticity operation, they support waves. They also support Rossby waves, but they are hidden. They're a little bit hidden because the first order waves that we can easily derive are other waves. So in order to derive the simplest way of waves here would be to assume a basic state that is 0. And that implies that, that phi has to be a constant in the basic state. Then this basic state would fulfill these equations. Yeah, if you insert this, the 0, and this is constant, then these equations are fulfilled. So, how do we find waves? The typical way is to we linearize our equation around this basic state. You have done this many times already. So how do we deal with this operator here? There are terms like du prime by dt plus u bar d, let's say du bar by dx plus only prime du bar by dx plus u bar du primed by dx plus u primed du primed by dx, and many more terms. Right? So many of these terms drop out because we've assumed that the basic state is 0. What happens to this term? If we linearize the equation, this term we assume to be small. We say, okay, we later on we want to impose some wave, and we keep that amplitude always so small that these second order terms will be much smaller than the first order terms. We say we try to control this. So we impose an amplitude that is so small that these nonlinear terms, they simply can be ignored. So in the end it turns out the linearization is really trivial, because the only thing that remains from the total derivative is then the local time derivative minus d phi primed by dx plus v naught d primed. We want to keep f as a constant. If we want Rossby waves, really f should be varying. But then the equation is not easy to solve, because then we have a linear equation in this case, but with not constant coefficients. We will deal with this case in the tropical, for the tropical Rossby and Kelvin waves. But here it's, for the time being, we don't have to do that. U primed and d phi primed by dt equals minus g, let's say the mean height of the system, du primed by dx plus dv primed by dy. So what do we do now? The typical approach that we do in physics is we try a wave solution. So we say u prime may be expressed as a and a wave I kx minus nu t. V primed equals to b I kx minus nu t, and phi prime equals c I kx minus ut. And then you insert this in this equation. That gives you, then you divide by the wave, and it gives you an equation for A, B, and C, essentially. 3 equations for 3 parameters. Now, obviously, we refresh our way to calculate the characteristic equation. There's always one trivial solution, which is A, B, and C is equal to 0. That's a solution. But we don't want to find that trivial solution. So then, if you do that actually, it's very simple, no? If we do that, we find, replace this maybe. The derivatives, the time derivative gives always minus I nu A equals to minus I k c plus beta mod beta, and then we get minus I nu b equals to minus f mod A. Because we assume that the wave, in this case, we keep it simple, the wave is just propagating in x direction. That's an assumption, otherwise there would be an additional term here. Minus I nu c equal minus g, the mean height I k a. So we solve this equation. There's a matrix applied to A, B, and C equals to 0. The standard way is that we demand that the determinant of this matrix is equal to 0. So we know how to do this. We can identify what it is. And the final outcome would be, you can almost guess what these waves are. The final outcome would be that the phase velocity mu over k equals this, or phase velocity c equals plus or minus square root of f naught over k square plus g times the main height of our systems. So if we ignore the Coriolis effect here, then what are these waves?
Gravity waves.
Gravity waves. Horizontally propagating gravity waves. Now in reality, if we assumed a compressible system where you can also derive the solution, then those gravity waves would also propagate vertically. But that approximation has filtered those waves already. So in this case, they don't propagate vertically, but they only propagate horizontally. So these are horizontally, in this case, even though just zonally propagating gravity waves. Gravity waves modified by the rotation of the Earth. Therefore, they are called inertia gravity waves. In this case, just to get an estimate on the speed of these waves, if we insert here the height of the tropopause, 10 kilometers. So let's say that would be this. Let's ignore this term here. So it would be even larger than that. But for the time being, make an estimate just with here. So that would be 10 times 10 to 4, 10 to 5 square root, 300 meters per second. Very fast waves. And these waves actually, they cause weather prediction a lot of trouble. Because these waves are so fast that you would have to, in order to integrate a weather or climate model, you would have to use a very small time step to be able to deal with these waves. You know this criterion, the Levy criterion, Courant criterion, where you have to adjust the time step according to the phase velocity in your system and the scales the horizontal scales. So, so large velocities, if you want to resolve them in your model, means that you have to have a very small time step. And that's the reason why many weather forecasting models and climate forecasting models, they don't actually use the momentum equation as it is, but instead they use the vorticity and some kind of filtered version of the divergence equation, which are equivalent to the two velocity components. The information they contain is in principle identical, only it's transformed in a way where it's easier to filter certain kind of waves. For example, these waves are kind of, for us, noise. They are not so important. Important for weather and climate prediction, more for weather prediction, let's say, are the Rossby waves that slowly propagate and determine our weather. These are just propagating very quickly, much too quickly to see any effect. There will be some effects, but it's not a first order effect. So that's the reason why we look at the vorticity equation when we derive waves, because applying the vorticity filters out these inertia gravity waves. It's just a filter, if you want a filter method. It doesn't contain these waves anymore. And the reason why we don't see Rossby waves is here that we have assumed the constant Coriolis parameter. Otherwise, in theory, there would be more solutions, and they would also contain Rossby waves, but they are very difficult then to derive. So now we repeat a similar analysis using, instead of the momentum equation, we use the vorticity equation.
I'm wondering how valid the assumption you're making is, because, for example, if you go back to the equation you had before, you had a change of velocity with time, which I assume is a much smaller component in regard to the component with the F naught and with the phi. It seems to be a much smaller component, because, for example, with the Rossby, when you neglect the nonlinear terms, you
Yes.
need to substitute the bigger terms in the places for the smaller terms to ensure a balance in the way that each one comes.
Okay, so which equation are you talking about? The du prime by dt, and then we have ignored like terms like, for example, u primed du prime by dx. And then that was balanced by d phi prime by dx, and there's the Coriolis term, f naught v primed. So you're saying it may not be justified to ignore these terms?
No, I mean, isn't even the term on the left, the rate of change of the velocity, much smaller than the terms on the right?
This is much smaller than this?
That's the question, isn't it?
How do you know? No. Okay. We can control our wave amplitude always such that these waves are small, because when we provide the amplitude, we can guarantee that the second order terms will be small, because they go with amplitude square. Okay, that's the usual linearization method that we use to derive waves. It's actually the only way easily to find waves, because otherwise we should solve a nonlinear system of equations which would be very complicated. So it's kind of a trick that we are using, right?
Time is very,
But-
very small.
Mhm. But eventually, so the fact that we solve the system means that these terms they contribute to the dispersion relationship in their way. So this provides the local time derivative, this provides some other term, the propagating term, and so on. So these terms, they're in principle all of the same importance in this equation. You cannot just ignore one of these terms. But the neglection of this term is justified by the fact that we can apply an amplitude that is small enough such that nonlinear terms are small.
Then that would mean that the time evolution is also very, very small to ensure that the first term is very big. Because if you make the u very small, because you want to eliminate it, it means the time evolution is really, really small.
No, the idea is really that if you insert an amplitude like we did, u prime equals to a, and then some wave, and then you insert this here, then you would see, okay, this is proportional to a, and this is proportional to a squared. If we now make a like 0.001, then this goes with the square of this. So it's that order of magnitude smaller than this term. So that's the way we can guarantee that these nonlinear terms are small. We get actually into trouble in principle as long as our solution in the end is really a wave type solution that doesn't grow, it doesn't decay, as long as our phase velocity is real. We can always define the amplitude so small that the nonlinear terms are not relevant. But if we find that the wave actually grows in time, that's maybe not the case anymore. Then the solution may be valid only for a very short time. Because then, if this grows, if the amplitude grows, then yes, we are in trouble at some point. But for the waves we have derived so far, that's not the case. So yes, no, should be justified. Yeah, this is, we have to get used to this concept. It's important for all kind of waves that we derive in the atmosphere and in the ocean. The linearization is a very, very, because my guess is in principle is the only way we can solve these equations. Because if we should solve nonlinear equations,
So we also limit it to scenarios without friction.
oh yes, no, we have ignored that here. Yes. We keep things very simple in order to derive something analytically. Of course, we always may argue, okay, but that's not the real world. But at least we may understand some features of the real world. Okay. That's clearly not the real world. But yeah, the amplitude of real Rossby waves may be not small, and we may come into some problems. But in the end, we will see the result that we get, particularly for Rossby waves, is justified if we compare it with observed Rossby waves, propagation speeds and so on. We find, okay, it seems that our assumptions were not so bad, because there seems to be some correspondence between our theory and real amplitude, real world Rossby waves, for example. But yeah, it's a good point. But the only other way we would have to solve these equations is numerically. But then you understand much less. Okay. Doesn't matter. Okay. Now we want to derive Rossby waves. So we go back to our vorticity equation. That looked like so that's a trick, of course. We use the vorticity equation. So the basis for the equation that you derive here is the following: is dH by dt Laplace square phi, the equestrian function, plus beta d phi by dx is equal to 0. So that was equation 14 that we derived in our lecture course. And now we make an assumption, actually, a more complicated mean state assumption, because it turns out that the mean flow is quite important. So we don't say the mean flow is 0. We don't have to say this. We can say the mean flow is such that the mean stream function fulfills the equation minus u bar y plus a constant, because then deep psi bar by dy minus is just equal to the mean flow. And this mean state, and we assume also that u bar for simplicity as a constant. Otherwise we run again into problems if we want to solve the following linear equations. If that's not a constant, we again have an equation with not constant coefficients that we will have later, the problem we will have later. But for the time being, we can simply assume here that u is a constant. Actually, when it turns out we want to deal with baroclinic instability, when do the waves grow or decay, we will have to use a different u bar. Actually, u bar that changes with height. But here, for simply Rossby waves, we can assume u bar is a constant. Then this mean state again fulfills this equation. Because if this is just a linear function, all these operators vanish, and this equation is fulfilled again. So this mean state fulfills the basic equation. But in particular, this has one advantage, because since we have here the Laplacian and here the d by dx, if we apply the Laplacian of psi bar plus psi prime, that's just the Laplacian of psi prime, because the second derivative goes away. And not only that, but also the d psi bar plus d psi prime by dx is just d psi prime by dx, because it's not a function, psi bar is not a function of x. That means the linearization of this of this full equation becomes very simple, because we know that we only in the operator, nonlinear operator here, the multiplication is nonlinear, and the advection operator, we only have to maintain the mean state terms, because this is already a first order quantity. So we can save a lot of energy and time linearization by linearizing this equation. So in principle, the linearized version then would look like a linearized advection operator. Beta deep C prime by the x equals here. So what happens to this term? It's also 0 because of the mean state. Deep psi bar by the x gives us v bar, and that's 0. So this term is 0 again as mean operator. So our linearized version of the vorticity equation now, where we allow a mean flow, looks like this. But we will see that the mean flow is really just like a Doppler shift in the end. It's just like to the wave propagation that we derive. It's like a additional velocity that we can have. There's not much more happening. So we could also assume now that the basic state velocity is 0. But it turns out later to define particular to define the group velocity, it's important to allow the mean state velocity to be different from 0. But we could set it for our analysis here also to 0. So what we do is we insert again a wave into this, because we want to try a solution that is wavy-like, and that leads us to the dispersion relationship. Very simple. The time derivative gives us minus I nu down here, and in the end we divide by the I. The x derivatives gives us ik down here. The Laplacian gives us, since we have assumed that in this case the waves can also propagate in the meridional direction, not only in the zonal direction, gives us minus k square I square k square, so minus k square minus l square plus k beta is equal to 0. So that's our dispersion relationship in principle, our characteristic equation. We have divided already by the wave, and we've assumed that our wave amplitude is not 0. Then this equation is to be valid. So it's actually a little bit simpler than our inertial gravity waves solution. So we can solve this for the frequency nu, and we can also use this total wave number abbreviation if we want to. And then we can find the phase velocity in zonal direction by dividing nu over the wave number in x direction, nu over k. And that gives us this expression. So this is the dispersion relationship for Rossby waves.
Excuse me.
Yes?
Here you're talking about the phi bar, which is in the zonal direction. Does it mean that in the meridional direction we don't have any changes, given the fact that Rossby waves are, we attain them by an assumption that we are assuming a change in the f0 factor, the covariance parameter.
Mm-hmm.
We don't have movement in the meridional direction.
These waves are allowed to propagate in the meridional direction, because we have assumed that there's a wave number in the wave number L goes in the meridional direction. Yes, that violates probably at some point our beta plane assumption. If we go too far away from our base point, the linearization, the assumption that beta is a constant, may not be valid anymore. So we cannot go to the equator for sure. And we cannot go too far away from our base point. Yes, you're right.
And does it mean that the u is both constant in zone meridional and in time.
The mean flow.
Yeah.
The mean flow is assumed to be constant in zonal direction, meridional direction, and in time.
Yes.
For this simple treatment, actually, there are extensions. You can make this problem more complicated and try to find a solution for varying mean flow quantities. But then this solution is not so simple anymore. And actually, changing mean flow is known to be very important to modify the propagation of Rossby waves. But here we are looking just at the zero order effect, the simply geometric effect of Rossby waves on a, in this case not even on a sphere, but in our beta plane, that essentially, yes, they propagate also in meridional direction here, but we, as you say, we have to be very careful because we have not assumed that they can propagate too far in the meridional direction. They can only actually propagate in some kind of channel that we prescribe. So ideally, we could even just say L is equal to 0 and just look at the propagation in the zonal direction, if we want to be stricter.
But we cannot use the momentum equation to derive them because the momentum equation has the component of a change in time, and if you use constant, it means that component vanishes and you cannot have a wave-like solution.
You can use the momentum equation also to derive Rossby waves. The system of equations becomes very, very complicated, but Rossby waves are also a solution of the momentum equation. Only that we have made our problem a little bit simpler by looking at the vorticity equation, or the stream function in this case, that filters out certain waves type, that, for example, the inertia gravity waves, that we don't have to deal with here anymore. But yes, the assumptions beta is constant and u are constant, u bar are constant, could be relaxed. If you are clever in math, you would probably try to find a solution for varying u and for varying beta. And then that would be an extension to this equation. And there are probably efforts in the scientific literature where people have tried to extend this in a way where u can vary. It's an important modification of the propagation of Rossby waves, actually. If you look in details. For the zero order theory of Rossby wave propagation, this is okay. But if you want to have small regional modifications of the propagation speed of Rossby waves, you should actually look at mean state flow that can change in principle. So you could define a mean state flow that is not dependent on time, but could be dependent on y and on x and on z. That would modify the solutions clearly, have important implications. But to a zero order, let's assume this. We also know that, coming back to the exercise that you did, if we indeed now assume that our wave is just propagating in the zonal direction, then this quantity here, this phase velocity here, inserted in that exercise where we calculate omega, would give us omega is equal to 0. Remember that? There was the solution was omega from P is equal to V k square C minus U. Should be U bar in this case, it's the same meaning, plus beta divided over F naught. If you insert that here, assume that k square is just a small k square, then this is 0. So that's consistent because we have assumed that the divergence term in our vorticity equation that would be on the right hand side that is proportional to the vertical velocity is 0. It's a consistent result. So this is the phase propagation of Rossby waves. What tells We have said this already in the last lecture. Very short waves. For short waves, k square is large. That means waves are mainly propagating with the mean flow, adjusted vectored by the mean flow. Long waves, for long wave where k square is small, then this term becomes more important. And there can be a wavelength where the waves are not propagating at all. Stationary waves. And this stationary wavelength can be calculated by setting the stationary with respect to propagation in x direction, by setting Cx to 0. And that gives us this relationship here. It's the definition of the stationary wavelength. Is beta over u bar. This is an important relationship because it tells us that in this simple formulation at least, stationary waves can only exist if there's a positive mean flow. Because if u bar is 0 or negative, this solution is not a real, this is not a real solution. Would be in imaginary terms here. So this can, stationary waves with the real propagation in x direction can only exist if there is a positive mean flow, eastward mean flow, westerly mean flow. It's a very important relationship.
Professor.
Yes.
I was thinking if a meridional Rossby wave arrives in a polar region, does it as a sort of reflection to account for some boundary condition? Or is it just that since the Coriolis parameter tends to constant,
Yes.
they are just how does it say it?
Yeah. We cannot deal with that question.
Damped waves.
Yes.
They move meridionally.
That's a good question. We cannot deal with this question here because we kind of have assumed that we cannot go too far away from our base point in the mid-latitudes. However, there's a famous paper that solves these equations on a sphere. And it turns out that these waves are propagating in great circles. You know, whenever you start, the great circle is the shortest line on the sphere of the Earth. You know that, and it's not a straight line. It's not a. You don't keep the latitude fixed, but it's a great circle. So in theory, keeping everything as it is here, u constant and beta according to its spherical value, then the solution would be that these waves propagate in great circles. And there can be things like trapping of these waves, actually, in the jet stream, for example. If you have a strong U flow in some region and then weak in others, that actually acts as a waveguide to these waves. So the waves can get trapped there and just propagate there. So, and then are reflected probably at the boundaries. So there are effects like that. But within our simple framework, the first order extension to the real sphere would be these waves propagate in great circles. Then if the mean flow is more complicated, but you have to use much more sophisticated mathematical methods then to derive that. Yes, there are theories that say if the mean flow is more complicated, then you can trap waves in that region where we have a strong jet flow. And those things are called waveguide. There are several of them. Yes. But for us, we keep it as simple as this. Okay. Again, the most interesting things will be an exercise, okay? Because here comes something quite important. You can show that the group velocity of Rossby waves is this. But you know how to do this. This is instead of nu over k, it's d nu by dk. So you derive the derivative. Is this, and you can show that the x component here for stationary waves is always positive. And this is another very important statement, because it says when you have a Rossby wave source, some kind of source that creates your Rossby waves, the way the energy propagates is always to the east. You don't have to look in the other direction. If you have a Rossby wave source, the energy propagates always to the east. That's important actually for ENSO teleconnections. We have an ENSO phenomenon, the wave propagates to the east. The stationary waves propagates to the east. North America and then even entering in Europe. We have an example for this later on. So this is a very important statement. Actually, there's this figure here which is not particularly nice, but let's try if we can understand what's going on here. This is actually a composite of geopotential height at 200 hectopascal for an ENSO event. So you collect many ENSO events. In this case, it's even a numerical simulation where you just prescribe permanently an El Niño and compare it with the control simulation. So what happens? Let's try to argue. So the heating is imposed in this model, but in the real world that would be this kind of an approximation to the real world. The heating, anomalous heating, is applied in this box here at the equator in the Eastern Pacific. What does it do? So the warming, essentially we prescribe a sea surface temperature anomaly that is a kind of increased positive anomaly. What does that do to convection? Increased convection, right? Increased convection means increased precipitation in that region. Increased precipitation will cause also the heating in the atmosphere to increase. You have studied that, right? Cloud, condensation in cloud is a heating term. So we heat more in this region than in other regions. So this heating term Q, due to condensational heating, also goes up. That may be compensated again by radiation, but it's not a first order compensation. Then remember our thermodynamic equation in the tropics. It was going like minus S omega is equal to the heating. So that means if the heating goes up, then omega goes down. Right? This is omega has to go down, but that means vertical velocity goes up, so it's rising motion there. So the first order equilibrium would be that in this region here, where we have the ENSO type SST anomaly, we get rising motion that compensates for that cooling due to the rising motion compensates for the heating that is imposed by the increased precipitation. If this vertical velocity, so let's say we have now this vertical velocity omega W here, hits the tropopause, what do we get? Divergent flow. So here's this tropopause, and the flow is often trapped here, cannot go into it. That the reason is that the stability in the stratosphere is so high that if you look at this equation, when the stability becomes very large, then the vertical velocity has to become very small. So this is essentially causing a strong divergence in the tropopause level, let's say at 200 hectopascal. So this is actually creating a Rossby wave source. On the vorticity, in the vorticity equation, on the right-hand side, now in the tropics there is a source term. There's a divergence, du by dx plus dVA by dy. There's an upper level divergence there that acts as Rossby wave source. And since it's divergence creates negative vorticity. It creates a negative vorticity which is represented here by this positive, actually, geopotential height anomaly. A positive geopotential height anomaly corresponds to negative vorticity because the flow flows around here in anticyclonic way, so this way. Then we can forget about to a first order approximation, we can forget about this forcing term once the wave propagates. So in the exotropics, these waves propagate according to this equation here. And it propagates, as we just mentioned, on a great circle. So we haven't derived it here, but this theory by Hoskins and Carioli, I think is the paper, they show that these waves should propagate in a great circle, which is kind of indicated here. I'm not 100% sure. It's a nice great circle, but so they propagate, for example, from the Eastern Pacific, modifying the Aleutian low into North America and into the Atlantic region. And by doing that, then they lose energy and power, disperse their energy. But so that's what these waves are doing, for example. There's one example. This is one important example how ENSO can create teleconnections. It's due to a Rossby wave train, to the energy propagation in Rossby wave, which is always to the east. Another example is what we are dealing with right now. We're doing right now, the forced topographic Rossby waves. So ENSO can create a Rossby waves from the tropics. But also orography can create Rossby waves. Why? Because again, on the right-hand side of the vorticity equation, when the flow goes over orography and we assume it's trapped by the tropopause, it has to provide a divergence term. The flow has to have a forcing term on this right-hand side here.
Professor, are these waves called the same barotropic Rossby waves, or
Yeah.
they can be also baroclinic?
These are, we are
Always barotropic.
barotropic. Baroclinic, we will touch a little bit. Baroclinic Rossby waves can also propagate vertically and can grow and decay. And we will see a little bit of this when we discuss the baroclinic instability, because we will solve again the dispersion relationship, but for the case where U is a function of Z, of height. And that means we have baroclinicity, because that means the mean state can vary in the meridional direction. There we will derive one very simple baroclinic extension of the phase velocity. It turns out the phase velocity is very similar, but there's for baroclinic waves in that simple form, you get something like, okay, U bar minus beta over K square plus something lambda square or something like this. That is a measure of the stability of the atmosphere. So there's some modification of the wave propagation.
I ask that because usually when you have those upward motion, you have like crossing of the isopiconals.
Yes. Yes.
In the ocean.
Yes, that's in the ocean. In the ocean, actually, we get an exactly similar formulation. I think we can do this. You can do the exercise for the ocean if you include that the height can adjust when there's baroclinic. It's not a baroclinic flow in the ocean, but if you take, it looks like this baroclinic adjustment. If you take into account the adjustment of the height, you get such a correction term. But yeah, okay. So for the time being, we don't have this.
For example, in the derivation of the same, like velocity equation, for example, in the ocean, we find that the sea in the zonal plane is always strictly negative, and therefore we always say they always travel westward. But
Yes.
saying they travel.
Yes, 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 very good. Yeah, I guess that's because then the U is so small that in the ocean Rossby waves always propagate westward. If U is small enough, then that's the case. So when you derive the Rossby waves in the ocean, do you set the U bar to 0, the mean flow? Do you remember that? I mean, the same statement is true here. With respect to the mean flow, Rossby waves always propagate to the west. It's the same statement. But if there's mean flow, that's not necessarily the case. Then short waves can be advected with the mean flow. And there's some compensation between these. Yeah, but I think in the ocean it's the case that the mean velocities are small compared to this term here, and therefore the statement is true that Rossby waves always propagate to the west. But the energy, even there, the energy always propagates to the west. No, cannot, because wait, there's more complicated because we don't have a mean flow. So stationary Rossby waves in that case don't exist. So I don't know about that statement. Yeah, because that statement is only true for stationary waves where we have a mean flow included, and then we can have a stationary Rossby waves. Yeah. So for the ocean, the situation is slightly different because of the smallness of the U. Whereas in the atmosphere, it turns out this U, which we assume again to be 10 meters per second, is a very relevant component with respect to this term here. If you insert wave numbers that represent waves of 1,000 kilometer wavelength. So these terms, they really compete with each other in the atmosphere. But in the ocean, yeah, the wave, this may be similar, this is of course the same, but the velocities are much smaller than in the atmosphere. So that makes a big difference.
Just to remember, I don't really see the U component on the equation. We only have the beta over the beta part.
Yes. The reason is that you assume that the mean flow is so small that it's not relevant, which is the case in the ocean. How much would be the mean flow in the ocean? 10 to not even 0.1 meter per second. I don't know where you are. What is the mean flow in the Pacific, in the ocean? I don't know, but definitely much smaller than 10 meter per second. Not even the Gulf Stream. You have 10 meter. In the Gulf Stream, you have 10 meter per second.
Maybe in the ocean, this could be a reason for the western intensification. I heard that there was some possible explanation in terms of these Rossby waves.
You have to ask Ricardo. I don't This I don't know. No, but that's a difference to the ocean. In the ocean case, you will not have this term. At least it's not a relevant contribution here. And then the statement is true. Rossby waves always propagate to the west. That we will actually come back to such an equation when we look at equatorial waves, because there we will set the mean flow to 0, because at the equator, the mid-latitudes the mean flow is clearly different from 0. But at the equator, the mean flow can be different from 0, but even the sign of this would not be very clear. It can be around 0. So therefore, for those waves, we set this mean flow to 0. Okay, if we now look at this, the forced part, so the forcing now for orography is that we have this forcing term on the right-hand side. So the equation we use is our potential vorticity conservation. expressed one over eta dh eta by dt equals to 1 over height d height by dt. And then you say this eta here that appears here for for our quasi-geostrophic approximation is nearly the f parameter, because the relative vorticity is much smaller, 1 order of magnitude smaller. You multiply that, you get the dh by dt, which in our case is only due to the bottom orography. And the h, you assume, is not really the total height of the system, but the approximation is the mean height that is not influenced by the orography. The orography change is so small that it doesn't influence the mean height of our system. So probably a 2.5 kilometer height that we have assumed in one of the exercises is too high. So maybe in this linearization purposes we can assume a maximum 1 kilometer mountain or 100 meter high mountain in order to justify to use a constant height here. But clearly, yes, if our height is 10 kilometers, we use a 100 meter high elevation or 500 meter high elevation, then this approximation would be justified. So you can just use a constant value here and a constant value here. Then we have a more complicated equation, because now this equation is not a, we have a forcing term on the right hand side. It's not zero there. And this function could be a mountain could be as complicated as you wish. It could be a nice little round mountain. In that case, you would have to solve this equation numerically, because you cannot solve it easily analytically. In order to solve it analytically, we have to assume a very nice mathematical but very unrealistic mountain, which is just a sine wave in x and in y. So something that is infinite, right, in both directions. Very unrealistic. The mountain would be confined. But then if you prescribe a confined mountain, that would involve a sum of many Fourier components to describe this, and that would make the solution much more complicated. So in order to find a simple solution, the best way is to try to prescribe a very simple mountain, a sine and cosine wave mountain. If you do that, you insert this on the right hand side here, you can try to find a wave solution that is going like this, in the same way as the mountain. And we assume that this wave is stationary already. So we drop the time derivative. So the wave, we look for stationary solutions. Then we can try to insert this term into this equation here, drop the time derivative, and see if we find a solution. That will work, because you can guess already. Here's an x derivative. Here's an x derivative that gives us the same kind of phase here. And here's an x derivative, and we have the Laplacian. The Laplacian applied to a wave gives us the same wave, with a changed sign. So that solution should work. And if you work that out, you find that then this amplitude that you have prescribed can be expressed as f naught times height of this mountain divided, maximum height of the mountain, divided by the height of the fluid times k square minus L square. So the solution over our mountain can be positive, can be actually in phase when we have ridges over mountains, are out of phase with our prescribed orography. It's quite interesting, depending on the wave number. So for example, we have seen that actually over the Rockies there was a ridge, and also over the Himalaya that means that solution is determined by short waves, essentially. We have seen this, here, and our perturbation of the geopotential height over the Rocky Mountains, there was an anomalous ridge, the ridging in the flow. And the same is true for the Himalayas, there is a ridging. So the solution here is governed by the short wave, by short waves, not by long waves. Otherwise we would have troughs here. The other interesting thing is that this equation allows for a resonance catastrophe if our waves are just the stationary waves, then the amplitude of our solution becomes 0. So that wave would explode. But in reality, of course, that's not the case because we will have some other damping terms. Okay. So as exercise, I just want you to do number 1, 2, and 3. Don't do the other. The exercise. Don't do exercises number 4, even though it's interesting, but it's complicated. In particular, number 5. Number 5 would be fantastic. It's the Rossby wave in a channel. Looking for numerical solution of Rossby waves in a channel. So if you solve that for me, it would be great. I would take it. But it's since it's a nonlinear, the exercise number 5, we are trying to solve the nonlinear vorticity equation. The solution has to be numerically, of course, but it becomes already, we try to solve Rossby waves in a channel, given that there's an orography, actually the same orography, no, slightly different. No, also sine, yes, the sine wave orography is prescribed, and then we try to find the solution. But if you discretize this problem, even with this two-dimensional domain, you will find that it gets already quite complicated. Also because you have to invert at some point. You have to invert. You find the solution for the vorticity, but in order to get from the vorticity the velocity, you have to invert the Laplacian to get first the stream function, and then derive the vorticity field. So that. It's complicated, but it's not. You can try. I have done it once. You can, if you want to do it for fun. At some point, it could be part of a numerical methods exercise. But for the next for Monday, I would just ask you to do exercises number 1, 2, and 3, and forget about the others. And then, indeed, in the next lecture, we will look at how we can find imaginary phase velocities. So where the waves, actually, these waves don't grow and don't decay, at least in the free Rossby wave case. But what additional ingredient is necessary to make waves grow or decay? That's done by the baroclinic instability problem, and we will discuss this in the next lecture. And after that, we go to tropical waves. Yes, Rossby waves, there are many interesting modifications to this simple treatment. So if you are interested in this, there is a broad literature that tried to extend that to make the mean flow, to see what is the modification that we can get when we make the mean flow meridianal dependent and X even zonally dependent. How can that modify the propagation of Rossby waves? Only for our lecture is too complicated. Yes.
Question here in the notes was I have how can you come from this to this? This is the well here's the fault. Here and the Kucharski notes same. You need to put here the equation.
Yes.
So this term is go away.
This term is removed by the continuity equation because you can replace yes minus 1 over rho d rho by dt. You can insert this here and try to combine with this term.
Okay. Expanding this term, you combine it with the other.
Yes.
Okay.
That gets you to this equation that combines the rho and the vorticity derivative. That's done by replacing this. Yes.
Okay, this is something just algebra.
And also this relationship here, you get from there to there obviously, because they are different here, no? Here is the density of the gradient, here is the, so in order to use this you have to expand this.
And to expand it and this use some equabilities.
Yes. Yes. Yes, because this is essentially we have gradient lambda. Now, in order to get this gradient out, then it applies also to this. So you have to remove, you have to use the product rule to
Get this triple product of Laplace.
yeah, this is easiest, you can easiest verify this if you expand this in Cartesian with t by dt.
That's not different the way.
And now you write, okay, this is equal to gradient u d by dx lambda. Okay, now this applies to both minus
alternative explanation just because
minus gradient u d lambda by dx, right?
I just say that
Because you applied here, you apply it to both. So you have to subtract that in order to get that. And these terms are the terms that you send C. Yes, these are these terms here. Because you multiply that scalar with the vorticity, but this is the gradient of the velocity field. And here you can use, of course, after this, you can insert here the total derivative of lambda, which is sigma.
Okay.
It's not difficult if you expand it in Cartesian coordinates.
It will be easy. That helps a lot.
If you want, I have it here. You can make a photo. Test it.
Exercise
3.
3. No, 6. Exercise 6.
Okay.
No, that's not an exercise actually. But I thought I counted anyway.
Okay, that's okay.
Maybe here.
This is it?
It's this one.
Okay. Okay.
Okay.
So
You
it's
can
good.
try to.
It's just for fun.
Okay.
Yeah.
That was today's lectures.
No, this is from the first lecture.
Okay. Well, talking about so you can divide by I side prime. Sorry.
Yeah.
So after all you derive it and you divide
Yes.
through by I.
Yes, you divide by
A.
yes, because if you insert this, what you get is proportional to A, I to the E, because that always stays, no? And then you get as a derivative I, for example, d by dt gives you an I, and then you end with the minus sign. And you divide by this, that's different from 0. You divide by I, and you say you search for non-trivial solutions. Otherwise, A equal to 0 is a solution. Otherwise, if A is not equal to 0, you can divide by it. And then you get to this equation.
Thank you, sir.